Hey, what's going on, guys? So for this week we're going to look at how a material responds when loaded under torsion or loaded with a different type of torque. So if you remember from last week, we looked at the tension capacity or the uniaxial behavior of different types of materials using the UTM. So all we did was just pull these steel members and aluminum members in one direction, uniaxial, and measured the strength or the stress versus the strain, the deformation of the object. So this week we're going to be looking at the torsion resistance of cylindrical rods. So these rods are going to be twisted and they're going to experience a type of shear strain. So last week we looked at normal longitudinal strain. Now the resistance to transverse motion is what we call shear strain. So we're going to be using this little setup here, and what we're going to do is just load under different torques, different twisting of three types of materials, and we're going to measure and ultimately find the shear strain of each material. Alright guys, so let's go over the materials for experiment 2, the torsion of a circular shaft. So this is going to be the apparatus that we're using to apply a torsional load or a torque to different types of materials. So it's pretty basic, but it gets the job done. We have 2 points where we can fix this metal rods in it. This little lever arm here is going to be loaded and apply a twist or a torque to the material. And you see we have this gauge right here, this dial gauge that will be zeroed out at the top, and it will be able to accurately and precisely measure the change of torsional direction or the twisting of our steel and different material rods. So what we're going to be testing is steel. We're going to be using a copper alloy, and then we're also going to be testing in aluminum. So we're going to find the shear strain and the shear modulus of each one of these three materials. So we're going to be doing that by loading it in different increments. We're going to use this little carriage. It's going to attach right there. This is 100 grams. And then we're going to be loading it at 0.5 kilograms, 1 kilogram, and 1.5 kilograms. And we'll use these different weights here to achieve those loading increments. So what I'm going to give you in the Excel spreadsheet is the load and then the deformation of each one. And I'll go through one example here just to show you how we would do this if you were actually here performing it with me. Okay, so let's set up the steel rod first, and I'll show you guys how we get our data. Okay, so what we need to do now is zero out our dial gauge, and we need to make sure that this level is as high as it is, or as high as it can be. So we're going to load, and this load is going to transfer and apply a moment to the longitudinal axis of this rod. Remember, a moment acting upon the longitudinal axis is called a torque. So we're going to measure this out, and then I'll go over and you'll see the data that I'm providing in your Excel spreadsheet. Okay, so we have our steel rods set up in the apparatus, and you can see I tried to zero out our gauge as close as we can. It measures a 0.000 millimeter precision. So this gauge is very precise, and it's very difficult to get it right at zero. But that's okay, because what we really need to find is just the difference between the initial value and then the reading once we load the torsion onto our rod. So the big thing that we're going to assume here is that all of the loading that is occurring right here is being transmitted into our rod. We're not losing any mechanical energy through this whole setup, which of course is not going to be the case. With these drills, the drill bit is not 100% like welded and attached to the steel rod. So it's not going to be transferring all of the energy. So account for that and make sure you mention that in our lab report. Our initial reading, what we're going to say, is at 0. So that's, or at 0.003 negative. So this is 100 grams. So here is 0.24. So we'll take that off. So the new zero is 0.002. And now I'm going to add 500. So 0.5 kilograms, 500 grams. You can see the value is 0.144. So we'll take this off. New zero, 0.004 millimeters. Just kidding, 0.003 millimeters. And now we're going to add another 500. So now this is 1 kilogram. That's 0.295 millimeters. We'll take this off. Our new zero is 0.001 millimeters. Now we need to add 1 kilogram. So this is 1.5 kilograms, so 1,500 grams. We're gonna add it right here. Oof. So remember, what we care about is the difference between this value and the initial. So when we unload it, you can see it actually doesn't go back to its initial point. Now we're still going to take that initial reading. We're just assuming that this deformation, this little permanent deformation, is due to the mechanical energy changing within our setup here, because again, this is going to induce a lot of error. We're not applying all of the energy to our steel rod. It's going to get lost through the gears and through the movement of material, metal on metal, that we see here. Okay, so I hope this little video helped to see how we're getting the data that I'm giving you in your Excel spreadsheet. Remember, big assumption, all the energy that we're loading on this level arm is assumed to be transferring into our steel rod. Of course, that's not going to be the case. And again, we need to subtract the reading value, or we need to subtract the initial value from the actual reading value to get that change in length. So by knowing the change of length here and applying geometrical properties, since we know the dimensions of this lever, then we can then find the torque or the twist that this material is being exposed to. So I did this for steel. I'm not going to go through the whole video, but it's the same step by step. I'm going to do the same for the brass, the copper alloy, and then also the aluminum, as they say. So same material, or different materials, same properties, and you're going to draw the curve and find each shear strain and shear modulus for each 3 of these types of materials. Let me know if you have any questions, and good luck.